Okay, we are going to start today's session. So we are going to continue with clustering. Just a review of the theory, and we'll continue after that to the questions. Okay, we had previously seen what is k-means clustering. So we're extending the concept towards fuzzy k-means clustering. So means like there is a chance in here that the data point may also lie in another cluster. So there is no hard margin between clusters. So that is why it is called fuzzy. So recalling, so k means is like this. So first you initialize the cluster centers, and then assign points to the clusters which has minimum distance with the cluster center, and you recompute the mean, and using that decide the next cluster center, and repeating this process until there is convergence. Okay, so this is k means, and so cluster centers are represented by theta here. Okay, so the cluster to which it belongs should have the minimum distance, and the data point should have minimum distance with that cluster with respect to other data points uh, to be into that cluster. So it has applications in image segmentation, like as you can see, we have clustered on intensity and color. Uh, so K means clusters application. Another application, as the number of clusters increases, the image compression improves. So how do we design the fuzzy one? So as you can see, we have defined here membership grade as UAX. Okay, and UAX is 1 if it belongs to that class. Okay, or that set. So in the case of k means clustering, it is called crisp set. Okay, and otherwise it is 0 if it does not belong to that set or class. Okay, and what happens with fuzzy k-means clustering is this this if the belongingness to a class may not be an exact 1, neither it will be exact 0 if it does not belong. It will be something between 1 and 0. Okay, so as you can see, so it can be anything from 1 to 0, and following this distribution. Okay, so this is the situation we have, and so we are actually, what we are doing is we are not uh, making a hard margin. What we are doing is a soft margin clustering. Okay, also called soft decision based partitioning. Okay, so for every cluster center, it has a different membership grade. All should sum up to 1, but none of them is equal to 1. Okay, so that is why how we are defining the problem. Next, what we have is so these are the cluster center theta 1 to theta k. Okay, theta j represent the jth cluster, and so as you can see, so this leads to a this membership grade matrix U, so having k values for each clusters. Okay, means k values for k clusters, and total samples are n, so n cross k matrix. And so this d x I and theta j, okay, theta j is the cluster center here, xi is the point that we have here. Okay, so d is the similarity between them, we denote it with d. Okay, so what we have done is defined a cost function relating this scenario uh, to represent the fuzzy distortion cost function. Okay, so as you can see, so this is the product of product of this membership grade, okay, and this similarity. Okay, so as you can see, if the membership grade is equals to 1, okay, this q is equals to 1, it is a hard decision or k-means clustering situation. uh, otherwise it is a, means if q is greater than 1, it is a fuzzy decision. And if q is equals q is infinity, or it tends to infinity, then it is total chaos situation, so it is not useful as well. Okay, so more than 1 but close to it is what is desirable. uh, so that is what is desirable, as you can see. So this is sum over all the cluster centers j equals to 1 to k, and then from I equals to 1 to n. Okay, so this represents the cost. Okay, which is the product of the membership grade and this d similarity that we have. Okay, or distance, that is what is, that is why the sign, okay, distance is what is used usually. uh, as you can see, as we sum from one all over all the clusters of this membership grade, we should get 1, because the sum should be equals to 1. Okay, that is the requirement, that is the definition of the membership grade. And this all are uij are between 0 and 1. Okay, so but if you sum over all the n values, it should be less than n, because each one of them is less than 1, so n times is less than n, right? So that is the constraints we have. We'll form a Lagrangian with this one, use Lagrangian multipliers. Okay, so next, moving on. So this is the algorithm we are following here. uh, so first we are taking some cluster center. Okay, random initialization is the best course of action. Okay, so starting with t equals to 0, what we are doing, we are running a loop for I equals to 1 to n and j equals to 1 to k. So now we are calculating the membership grade. Okay, so how is it calculated? So you can see it is 1 by summation over all the cluster centers. What we are trying to see, as you can understand, uh, this is the distance between the xi point that we have. Okay, for this I, this xi point. Okay, and the jth cluster center, that distance we are calculating. Okay, or the similarity, as they say. Okay, and it is divided by this pth cluster centers. Okay, and we're summing over 1 to p equals to 1 to k. Okay, so this is how this product is carried out. Okay, so as you can see, this dxi theta j t, this is not dependent on p, so we can take it out of the summation. But rest is dependent on this summation, dependent on p. Okay, uh, so that is how we run the two for loops. Okay, for j and I. So that is how we run the two for loops for j and I, and we are able to calculate this uij. Okay, so what does it actually mean? So we are calculating the membership grade for ith data point and jth center. Okay, so that is what we're doing here. Next, as you can see, we had another loop t equals to 0, so we keep incrementing that. Okay, so t is the number of steps till convergence. Okay, so in what you see inside t loop, what we are doing is we are varying from j equals to 1 to k, means we are moving along the all the cluster centers, and we are calculating this theta j. What is this theta j? Theta j is here, as you can see. So we are updating the theta j, that is the estimate of the cluster center. Okay, so how we are doing that? So we have got this uij, okay, power to the power q, and this t minus 1 is here, and it's like average over average having weights uij q t minus 1. Okay, so that is how we get the theta j. Okay, and so this has to repeat till convergence. This eta value should be as small as to our liking. Okay, so this is the idea. So this is our cost function. As you can see, we have defined it before. So derivation of this membership grade we are trying to find out. So this is optimization problem. The constraints we change it to a no constraint optimization problem using a Lagrangian multiplier. And then we differentiate with respect to our variable, that is this one, membership grade, at which the cost function becomes minimum. That is how we got the expression of the membership grade. Okay, as you can see the derivative. Okay, with respect to this, so q will come forward and this remains the same, and then this summation only lambda r will come out. Okay, simple. So next what we do is, so this part we have got it. Okay, so let's look at some questions around this. uh, this is one of the fuzzy k-means clustering problem. So like, which clustering technique is better when there is overlap between clusters? So the fuzzy k-means is the better one, because it assigns there is other possibility of happening to of the data point being in another class, and assigns, as you can say, a softmax score type. Okay, so it belongs, the highest one should be taken seriously, but it also signifies that it may belong to other cluster as well. Okay, so how is the centroid of the cluster is calculated? By summing the membership weights along with means membership weight are to be used as weight along with the coordinates of the data points. So that is how we calculate the as I will show you here. So this is the one, you can see uh, this this weighted mean is what we are talking about here. Okay, so this is how we calculate the cluster centers, which is the weighted mean of the data points having the weight, this one, what do you call this, This is membership grade as the weights. Okay, so that is how we come to this. Next question is, so this one is done, right? And okay, not working. So this one is done, right? So this is the option, summing the membership weighted coordinates of data points, right? Next we move to the next problem. Which parameter in fuzzy k-means controls the fuzziness of the cluster? Okay, so it is equals to this exponent. Okay, the exponent of the membership. Okay, membership, what do you call that, uh, membership membership grade. The exponent, as you can see, this is the q. Okay, so this q is actually deciding what is the fuzziness. Okay, another one is, acha, this is the membership grade. I'm sorry, got it wrong here. So this is the membership grade, and in the cost function, as you can see, this exponent is actually deciding the fuzziness. Okay, so that is what they have asked, and you can see that it is okay. Next we move to this problem. Okay, no more on this one, so we move on to the next topic, that is other clustering algorithms. So let's download this one first. Okay, so we get to another clustering algorithm, which is hierarchical clustering. uh, what does it mean? So what we do is we take each point as a cluster of its own. Okay, and then repeatedly merge the closest to cluster. And closest, by closest what we mean is suppose the distance, it can be mean distance, max distance, whatever it is. Okay, so that is there is some criteria to merge the data points. Now next what we have here is, so 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 as you can see, we have to merge the two closest criteria. Okay, and we have to keep record of the clustering as well as the sequence of cluster operation. Okay, while coding this one. Okay, what we get is a resultant diagram called dendrogram. Okay, so what does it mean? Okay, so see, so as you can see, these two are very close. Okay, so these are clustered into one. Next, these two are close, so they are clustered into another cluster. Okay, after that these three are closer. Okay, so these are the ones that comes up. Okay, so building up, we get this dendrogram. Okay, so closest one are more similar. Okay, so similarity is 0, means that dissimilarity is 0. Okay, so that is how, as we move up, the dissimilarity increases. Okay, so so uh, that is the thought process in this algorithm. Next, what we do is okay. So let's continue. So next, what we need to understand is the what can be the criteria upon which you're clustering is average distance of point between points, maximum distance, minimum distance, likewise. Okay, can be distance between means as well. Okay, like that. Now what we have here is how many clusters there can be. Okay, so cluster depends on the number of um, dendrograms. Okay, so what we have to do is the our thumb rule should be how many clusters do we want. Okay, so as you can see, we have a stopping criteria here. Okay, which results in 4 clusters. Okay, it's got the idea. This is stopping criteria resulting in 4 clusters. Okay, if it stopped beforehand, it could result in more than 4 clusters. If it's stopped even later, can lead to only one cluster. Okay, now now what we are doing is this distance or this similarity criteria, we are focusing more on that. So cluster based on the minimum distance. Okay, so what does it mean? So these 2 points have minimum distance. Okay, so okay, so they come under one cluster. Maximum, what we are doing is that so so this one should be different from the cluster. Okay, not from the other one. Likewise, average and mean. Okay, mean between centers. Okay, the interesting thing is this distance produces the minimal spanning tree. Okay, okay. Uh, so this agglomeratic clustering are widespread application. Um, Hierarchy of clusters happen. We can control the cluster. Okay, uh, but we have to still choose the number of cluster or threshold here. Okay, so that's the problem here. Next we are focusing on this mean shift clustering algorithm. Uh, so, so what is the point of view here? Is that first we are taking a region of interest. So this blue circle is the one, and we are so the center of this circle is the okay, just the center. Okay, centroid you can say, and and we calculate the center of mass of the points, which will be at some distance from the center of the circle. Okay, so what we try to do here is that at every step we are moving the region of interest towards that center of mass. Okay, so we're moving this center of the circle towards the center of mass at every step, as you can see. So what does it result is that it results to the center of the circle shifting to the mode of the probability density function. Okay, so what does it mean is that that point has the highest density of points. Okay, and so we need to non-parametrically estimate the density gradient. Okay, density means that derivative of the PDF. Okay, so we have covered Parsons window before. We're going to use the concept from there, and the point of view is this: the convergence happens at the mode of this PDFs. Okay, so there are two modes here. Okay, multimodal data. So there are uh, convergence to 2 points. Okay, so how do we do it is that this so is it is the px is defined as this average of the average of this kernel. Some kernel has to be there. Okay, so using okay distance. So we calculate this px. Okay, okay, and this x is, I think, this one, center of the um, region of interest we have. Okay, so px we have. Okay, and so there can be various kernels for our use. Some radial basis function, uniform kernel, normal kernel. Okay, so this type can be there. Okay, next we need to find this delta px. Okay, and so this is the kernel we have defined is like a norm of the distance between the center divided by h is the size of the window or bandwidth parameter. Okay, taking derivative, it comes out to be this. Okay, where g is the derivative of the kernel function. Okay, and used like this. Okay, so this so this has to be calculated to get delta px. Okay, which represents the new kernel, means it represents the new what do you call that, cluster center. Okay, okay, okay. So we calculate the mean shift like this. Okay, so first, okay, so subtracting from the earlier kernel center produces the shift. Okay, so what you have to do to get the new kernel center is add this mx to the previous kernel center, not kernel center, cluster center. Okay, okay, so that is we have done. So we calculate this mean shift vector, then we add this to the kernel we have. Means we add this to the cluster center to get the new cluster center. We repeat it until delta px doesn't become 0. So as you can see, it is particularly useful when the clusters are of different shapes. Okay, as you can see, some image processing application. You can see we can cluster this. Okay, segmentation can be done with clustering. So that part is explored here. Next we get to the problems here. So what is the main objective of the hierarchical agglomerative clustering? So what we are doing is that it maximizes the between cluster variance. Okay, so this is the idea how. So we are dividing the all the data points into new clusters. Okay, and then we are joining them together. Okay, so the clusters which have more difference are divided into different clusters. Okay, so the variance between the two different clusters is more. Okay, that is the thought process here. Maybe a little difficult one to guess. Okay, so mean shift clustering, as you could see, it handles clusters of different sizes and shape, as I've explained. Okay, next what we have is uh, okay, this kernel is the shape of the density function here. Okay, and the bandwidth parameter in mean shift clustering. So this bandwidth parameter is the yeah. So from the Parson window lectures, you must remember the bandwidth size is the size of the search window around the data point. Okay, so this is the one. Next we have this question, which is a bigger question compared to what we have encountered so far. So it is a numerical. Okay, so this kernel is this one. 1 minute, I use that. Okay, so this is the kernel function we have here. So let's see how we use this one. Okay, this bandwidth h is given as 2, which we use, and other we have to do it, right? So first things first, so let's see the formula what we have to use. Okay, so So this is the formula we have, and this g function is what? G function is the derivative of the kernel function. Okay. So first we have to calculate the g function. So how do we write gx here? Gx is equals to exponential derivative remains the same, but by chain rule we have to do it. So what will that be? Minus x by h. So this is derivative we have here. And next what we need to do is, okay, so this is gx we've got. Okay, actually negative has to be there. Okay, so this becomes positive then, and okay, so this is our gx, and we have to calculate this distance with the initial value of the centroid from every other point. Okay, so that is important, right? Hmm? Okay, so next what we do, so we have to calculate this one. So let's see the equation. Okay, so this norm square is required. Okay, L2 norm square, which is the square of the distances. Actually, first we need to need initial value of the centroid. If nothing is given, we take the um, mean of those points. Okay, so question is where here. So mean of these points is, so first x bar we have to take, that is equals to 2 3 5 5 to 7 7 6 10 13 20 28 by 6 28 by 6. Okay, and another coordinate is 6 2 8 8 16 16 24 and 9 is 33. Okay, so this is what they have used as x. Okay, so these are initial centroid values. Okay, next what we'll do is calculate this one, right? So what is this distance? Okay, okay, and we have to divide by 2 in each distance calculation, h. Okay, or if we try to do it, h or h square, h square should be there, right? Yes, so divided by h square here. Okay, so what it will result in this, and you have to put it into this formula. Okay, okay, so maybe I'll show you some of the calculation. Any doubt up to this point? Any doubt? Okay, Okay, let's continue. So so this is the kernel we have. Okay. Okay. So what you should do actually in this situation is to so you have to use this one gx, right? So and what you need to calculate here is gx minus xi, like this. Okay, I need to sum over it, right? uh, so okay, so we need to sum over this gi, right? This is important, and h is also important, I think. Acha. What is it? Acha. Acha, h is automatic there. I think we don't need to use that one again. uh, just this one, right? Okay, and sum over it over I, number of data points. Okay, so for I equals to 1, let me show you how it will be done. Okay, so not a bit right. What happened? Some problem, I think. Not able to write somehow. Maybe I can use a new blank slide here. uh, so what I was trying to do here is so calculate g for I equals to 1. We are trying to calculate. Okay, so what we're going to do is this presentation we have, it's a struggle now. Let's see, maybe we can write it now. No. Okay, so let me first write down the gx function, which is equals to e to the power 0.5 x by h square x by h 5 x by h square x by h. Okay, and this has to be like when you're calculating gx minus x1. Okay, what will this will be? E minus 0.5 x minus x1. Okay, so x we know, x1 has to be 2 point okay, so what we're going to do, x1 first component minus 2 square plus x2 is the second component minus 3 square. Okay, this is the one. Okay, next divided by 8 square, that is 4. Okay, this one is done. Next what we do, okay, able to write now, I think. This is the one, right? Somehow it got resolved on its own. So next what we do is we okay, so this is incomplete, as you can see. This has to be multiplied by x by h. Okay, and you must understand this will be x minus x1 by h. This has to be norm 2 without the square. Okay, so what will it be? H will come out as 1 by 2, and this will be under root x1 minus 2 square plus x2 minus 3 square. Okay, this has to be calculated for each one of them. Okay, next what we have is we go to this problem, this expression. So this summation over gy is done, right? C is the normalization constant. You don't need to worry about that. Okay, the kernel has already been given. Okay, so that is from where the C is coming, so you can ignore the C part. Okay, this is the summation over xi with the value we get from gi over n. Okay, and then subtracting the initial value of the centroid. Okay, that is how we'll get the mx part, m value. Okay, and adding that to the initial centroid value, you'll get the first step. After first step, what is the value? So this is how it should be done. Okay, any doubt? Any doubt? No doubt. Okay, so this x by h, as you can see, has to be under L2 norm, because in this formulation we have used L2 norm as the one. Okay, as you can see, this is the okay. So if it is not square actually, so then it has to be an L2 norm. Okay, okay, if it is square then it is simple, but from the derivative, as you can see, we get the non-square terms. Any doubt? So happened very quickly actually, under 1 hour, all done. So solve this problem, get the answer. Okay, don't leave it where I left. Okay, okay, so we finish up here. Thank you everyone. So anything to say, anything more? Nothing. Okay, so we finish up here. Thank you everyone.